So as I said, I'm Rob Hague. I'm CTO at a company called CyberEve, and I'm going to give you a bit of a rundown on how we use TypeScript in a slightly unusual context. So first off, a bit about the company. We're an early stage software company based in the UK. We've got about 30 people. This is our office. It's a converted watermill. It's just outside Cambridge. And we were founded in 2012 by Tom on the left, who's a vascular surgeon. Tom Carroll, he was at Guy's St Thomas's Hospital in London, and he was encountering particular problems in his clinical practice. So he asked around, and he eventually got together with Graham Penny on the right, who was an imaging scientist at King's College London. So they founded the company in 2012 to establish that the technology was viable. They figured out it was. They got it to the stage where it was working, but they then needed to set it into a product so we can deliver to clinicians. And that's where I joined the company in 2014. So the product is CyberEve. EV stands for endovascular. I'll explain that in a moment. But what it is a software medical device that provides augmented reality overlays during image-guided surgery. And here it is in action. So you see the little display in the middle. That's CyberEve being used in an actual case. So it's been FDA cleared and CE marked. It's used in regular sort of clinical use in a lot of sites in the UK, in the US, and across continental Europe. So to explain exactly what you're looking at there, I'm going to take a slight diversion into surgery. So one of the key diseases we support the treatment of is abdominal aortic aneurysms. So the aorta is the main blood vessel coming from the heart that starts pumping oxygenated blood through the body. An aneurysm is where the wall of that vessel weakens, and it causes it to swell, and if left untreated, it can burst. In case of an aortic aneurysm, that's often fatal, so you don't want to let it get to that stage. So the treatment is conceptually very simple. You get a cloth tube, a graft, and you implant that across the diseased part of the blood vessel. What that does is blood then flows through the tube instead of into the aneurysm, takes the pressure off the aneurysm, and it can stop expanding or start to heal. So the question is, how do you get that graft in there? One option is open surgery. So you literally cut the patient open, the surgeon sews in the graft directly, which that works, but it's a very major procedure. It's very traumatic for the patient. And has a very long recovery time. So a very attractive alternative is endovascular surgery, which looks a bit like this. So for endovascular surgery, what you do is you augment the graft with basically a springy metal frame, a stent. So you produce a stent graft, you just crunch it down, kind of like an umbrella, and put it inside a tube. You insert that tube through a small incision in the leg, so it goes up the femoral artery. The clinician threads it up into the location it needs to be deployed, withdraws the tube, and it springs out like an umbrella and fills in bridges the diseased part of the blood vessel. So that is a far quicker procedure, or not to say quicker, but it's a far less invasive procedure, less traumatic, far quicker recovery times for the patient. The problem is, you can't see what you're doing. If you're doing open surgery, it's right there in front of you, but here, all you've got is you have this device you're kind of inserting into an incision, and you just see, the only control you have is basically forward and back and twisting, but you need to position these very accurately as well. Because if you look at this diagram here, you see just above the graft there are these two vessels coming off. They're the renal arteries. If you block one of those off, you're going to lose function of the kidney. So it's vital that this graft goes exactly where it's meant to. In slightly more complicated procedures, if the aneurysm was higher up, the graft would actually have little holes in, or branches, and these need to be positioned exactly into the vessels so that you don't cut off blood flow to them. So these procedures are done, you need some way to obviously see where your device is before deploying it, and these procedures are done under X-ray guidance. So this is the typical fluoroscopy image that you'd see during a procedure. And you can see on here, you've got the bones very clear. This is partway through a procedure. You can see the device. You've got a stent graft, which is this the mesh part in the middle. And you can see, in fact, there are some wires going into the renal arteries in this image. So, so you want to spot where you can't see on that image. You can't see the blood vessels. It's a problem because blood vessels, everything else in your abdomen, that's about the same density as far as X-rays are concerned. So you can't see soft tissue on X-rays. There is a way around this. You can inject contrast medium, which is an X-ray opaque fluid. It shows up lovely, nice, clear picture. It shows you exactly where the blood vessels are. The downside is that's toxic. That can also damage your kidneys. So you want to do that as little as possible. So a technique that's used to get around this, and this is where SADA comes in, is to overlay other information onto this image. So the other information we use is the preoperative CT scan that has been taken before the procedure. And this is what's been used to diagnose the disease in the first place and plan the operation. So this is already existing data. So we take that, we segment out the bit of anatomy that is interesting, and we combine it with the fluoroscopy image. So here you can see this is the output of what the surgeon would see with SADA Medical. And you can now see the blood vessel, see what it is, and you can confirm that the renal arteries are where you expect them. So obviously this is a big benefit. The big benefit to the patients and to the surgeons, it uses you have to use far less contrast medium. You also have to use fewer X-rays, which is a big benefit for the patients. Also a big benefit for everyone else in the room, because increasingly the patient will have one or two of these procedures in their entire life. Everyone else in the room is doing several of these a week. So even though they're not directly in the path of the X-rays, the backscatter of the X-rays is quite an issue. So a system like this can reduce X-rays, and that is very important for everyone in the room. So there are other systems that do this on the market. They tend to be based on mechanical tracking, which is, it works, but there are two disadvantages compared to how we do it. So the mechanical tracking systems track the relationship between the X-ray set and the table. So as the X-ray set moves, it knows what angle that is to the table, and it can update the overlay. What it doesn't know is how the patient is moving relative to the table. So that's the source of inaccuracy, and we are far more accurate than them. And also, there's another problem, which is these mechanical systems are part of very expensive fixed X-ray sets that are installed in the operating room. Our system is retrofitted could be one of those sets, or it could be a far cheaper X-ray set in a regional hospital. So we will work with essentially any X-ray set. How we do it is we use cloud computing to apply computer vision. We find the vertebra in the image, and we match those to the vertebra in the CT scan. So from that, we can work out what the projection of the CT scan, what the projection of the fluoroscopy image is. We do a similar projection on the 3D information from the CT scan, and we can produce this overlay. So that's the surgical part over. That's the product. That's what we do. So how does this look in practice, and where do we use TypeScript? So I'm going to take you through a few of the parts of the product, and I'll point out where we use TypeScript. Here, this is what we call the Vault. This is a system. This is the part of the tool that the clinicians log onto on their desktops in the hospital. They can upload scans they want to use with the system, and they can interact. They can see how they're progressing through the system. So this is essentially a fairly conventional database-driven web app. But the front end, we've added quite a bit of interactivity. So one example is these images at the bottom you can see. They are, you can scrub through them to make sure you've got the right image, because it actually annotates these ones. You might upload several CTs for the same patient, not all of them are suitable. So this allows you to preview them, figure out that you're getting the one you want. So TypeScript, and all of this is a place where TypeScript is particularly useful, simply as a better way to write JavaScript. So all of this kind of thing is fairly bread and butter, interactive web page JavaScript stuff. But writing that in TypeScript is just a better experience. The translation is quite useful. It means we don't have to have a separate compatibility translation step. And it just basically makes it easier to organize and easier to keep track of. So that's one part of the interactivity. The most interactive part of the vault is this, which is called the overlay creation tool. So this is a 3D viewer and sort of annotation tool, which the clinician uses to take the scan, select the anatomy they want to see in the operation, and you see there we've picked out the aorta there, and you can see the aneurysm. So that is something if there's this kind of thing, you'll typically have a separate workstation for this kind of application in the hospital, and you have to go and sit at it. We didn't want that. We wanted people to be able to use this from their desktops anywhere they were sitting. We didn't want them to have to go to a specific, like a special room to use the segmentation workstation. So how we did this is we considered it as a purely as a web app, but the main problem with that is you can't rely on the clinicians having a decent computer on the desktop. In fact, they almost certainly won't have a GPU or dedicated GPU. So as an alternative, we've taken a remote desktop approach. So the main application in the middle is a C++ application running on an AWS instance in the cloud, which has, has enough CPU to handle this, has a decent GPU. So we can give a sort of consistent level of performance. And we deliver that via a VNC session in the browser. That, the VNC viewer itself is off the shelf, but around that we've got a fairly complex bit of TypeScript, because it turns out when the trade-off is you've traded local performance of the machine, which is now doesn't really matter, but what does matter is the network performance. So we've got quite a lot of logic in there to track the things like disconnections, if things slow down, if things get, if basically one thing that seems to frequently happen is the connection pauses and resumes, but never actually officially sort of properly closes. So there's quite a lot of logic in detecting that kind of event and responding to it correctly. And these are found that it was a lot easier to keep track of this if it's in TypeScript rather than trying to do it all in vanilla JavaScript. TypeScript is very useful for imposing a bit more organization on that and keeping track of what's going on. So the final bit is once you've done all this, you actually go into the operating room. And this is running on basically a touchscreen PC. That's the thing we saw in the first photo. So this is the interface that the clinicians will be looking at while they're operating. So we have this. The fluoroscopy is coming in via a video feed, so via a video capture card. And we take snapshots of that, send them up to the cloud for processing, and get back and display the results. So obviously this isn't something you do with web technology, but nevertheless, that's what we did. So all of this is running in a standard web browser on this standard PC in the operating room. So that raises a couple of questions. Firstly, how? Now, yeah, I'm sure you're all familiar with the web platform, so I think you're probably preaching to the choir. But this wouldn't really have been feasible in, say, 2010. But now, the web platform's got increasingly powerful and has got a lot of capabilities it didn't used to have. So, for example, WebRTC, that allows us to capture the video without having external or special software. WebGL, obviously, we use that for rendering the overlay itself. And even the outline overlay, that is a full 3D render with a special shader. And WebGL has been proved very powerful for that. WebSockets we use, obviously, for more dynamic communication. And probably the most important thing is maturity and performance. So on the maturity side, the web platform has rounded out things like promisers, typed arrays, that kind of thing, they've become widespread and mature, stable, and gives you a very strong base to work on. And the performance, I think, has been incredible. There's been a very virtuous, a lot of virtuous competition between the major browser vendors, and the performance of JavaScript is now phenomenal compared to the other major dynamic language you use is Python, and yeah, there's no contest. JavaScript is far better in terms of dynamic language performance, just far faster, and this is because there's so much competition amongst browser vendors. That's worked out really well. But I suppose the bigger question isn't so much how as why. Why did we take this somewhat unusual approach to what would, in most contexts, be an embedded system that you did in C++ or a native toolkit? So, to represent this definition, key part is we want to be a software medical device. So we didn't want to be a hardware company. We wanted to be a software company, move at the kind of the speed of a software company. Because you can do hardware at a small company, but especially medical hardware, that is a very tough proposition. And the regulators, so we have FDA, we have a 510K clearance from the FDA in the US. Europe, we have CE mark. The regulators are starting to get up to speed with the idea that you can have a medical device which is purely software. This is a relatively new thing. For a while, we were working on from 1997 on the checklist. So every time we had a release, we had to go, okay, does this change the sterilization, the sterility of the product? Do you need to make a change? It's like, well, you can't really sterilize software, so no. There's now a special, it's a different software. If you've got a purely software medical device, there are different checks you do. And for example, is this change to fix a security flaw? Then essentially, don't need a new 510K. If you are making a change to fix a security issue, they say, get that out. That is something that you can do. So the regulatory agencies are becoming far more aware of software as a medical device. But the key is we don't want it to be just the software, not the hardware. So if I take you into the medical room, our setup is we would have an existing medical device. This is the X-ray set. So that is a classroom medical device, obviously for obvious reasons, because it's got shooting ionizing radiation at people. That is very highly regulated. A very involved process to get the certification, and if you modify it at all, that would potentially invalidate the certification. So we don't do anything to potentially modify that device. Fortunately, there is a standard feature on these is a video feed for a second monitor. So that's what we plug into our capture card. So we can access the pictures from that device without impacting its certification. So on the other side, we have Cyber Medical and we have CyberEve. CyberEve is inherently a cloud system because we need a very, very large amount of compute to do the computer vision part. So we've always been had it as a cloud system because we don't want to be delivering this compute hardware into hospitals. And that is a medical device in its own right. We do the certifications for that. That involves basically having a QMS, it's a lot of process, and you have to have a well-established process and do things. The key thing is risk assessment, and it's a risk-based approach. So we maintain the certifications for that. In the middle, you have this, what we call a Cyber appliance. This is a standard PC running standard software. Therefore, that in itself is not a medical device. So this, we just get it from a supplier. It has to conform to other standards, like the key one is it needs to be cleanable if it's in an operating room, which means it has to be fanless. That has a surprising impact on performance. If you compare the real-world performance of a fanless machine to exactly the same hardware but cooled, you'd be surprised at what a difference that makes. So that's something we've run into. But this is essentially a standard PC. Because of that, all of our software is in the cloud side. But what that means is we need a platform where all the software lives on the cloud side. The PC, the hardware in the operating room, is just a dumb terminal essentially that's bringing the hardware in and displaying it. Bringing the software in, running it, and displaying it. And for that, the web is an obvious choice. So I'm going to have to speed up because I'm running out of time as well. So how do we get from? So we've got the web platform. That's why we chose that. How do we get to TypeScript? Well, we start off thinking, okay, most of the sort of heavy lifting is being done in C++ and Python on the server side. So we've got JavaScript. That's just going to be doing something fairly simple, very simple, straightforward client, and that's going to be bringing things from the, getting results from the server, displaying them to the user, sending video frames to the server for updates. And that's the first version of the system that we produced. That's how it worked. But we rapidly realized that we were going to have to do a lot more on the client for two reasons. One, performance. You don't want that round-trip latency every time. If you can do more locally, you can react to changes quicker. But also safety. So remember I said a risk-based approach is a key part of getting your medical device certification. One of the risks we identified is showing the wrong overlay. So if we can have a check that the overlay that we're displaying corresponds to the image that is on the screen, if we can do that locally, we can enforce that safety constraint far more reliably. In particular, we're not relying on the network to enforce that. So that is a big win for us for safety. But we had this, and we developed this in JavaScript, but by the time we'd added in this extra part of the computer vision on the local client, that was getting very unwieldy. So we had a look around for options to replace JavaScript. So CoffeeScript we dropped quite quickly because didn't really offer us anything over ES6. And yeah, even so we thought, well, whether or not you like the syntax, the actual benefits, it was clear that ES6 was going to be widely adopted. So yeah, if we were going with CoffeeScript, we may as well just go with modern JavaScript. So that left the other two options, Flow and TypeScript. So this was a far harder choice because the two systems, certainly in 2016 when we were making this decision, are pretty comparable in terms of power and expressiveness. It boiled down to two things. One, I prefer the syntax of TypeScript. That wouldn't have been, it's nice to have, it wouldn't be enough on its own. Two, tooling. Even then, TypeScript's tool I think was better than Flow's, and it's just gone from strength to strength since then. But a key one as well, this is a bit of a gamble in 2016, is popularity. We wanted to be on the one that was going to have the broadest community and basically we didn't want to be in a sort of like a niche interest a few years down the line. And that was a bit of a gamble in 2016, but I think it's fair to say, yeah, that's paid off. So I think, yeah, TypeScript, both, yes, taken off clearly is the winner in terms of popularity, but also it's worked really well for us. So I'm okay to go a couple of minutes over? Yeah, cool. Right. So we'll not go into too much detail, but basically we found the conversion process was very straightforward, just at fast time. As soon as we converted everything, we turned strict mode on, and we kept that on because basically that gives you the most benefits from your types. And yeah, it's proved very useful for us. It's one of the things I particularly like about it is the combination of functional and object-oriented types. So many years ago as an undergraduate, I learned ML, and when it came to TypeScript, I kind of dug that knowledge out, and I've tended to do TypeScript in a very functional style with algebraic types, and yeah, I really enjoy that. It works really well with the way I think. But other people on the team did it in a more sort of Java or C# style with classes, interfaces, that kind of thing. And TypeScript not only allows these two things to coexist, but it allows them to integrate. And so we could obviously have a coding standard that said you were not going to use this algebraic type, so you're not going to use classes. But we found that's not been necessary because the 2 bits of code, they will actually work together really well. I think that's one of the big strengths of TypeScript's type system in particular. And the last thing I want to go over is one particular thing that we found. So once we converted to TypeScript, everything was a lot more manageable, but it's still quite complicated. It's still quite difficult to understand what was going on and reason about what was happening with the system. This so this was becoming a problem because we obviously need to be confident that, again, this invariant that we don't display the wrong overlay compared to the image. We want to be absolutely sure that that invariant holds. So I looked around for options for how to kind of organize the code, and the one we came up with is Redox. So this is one of there's several similar things around, which is essentially a functional approach where you have a combination of states, a state tree which is immutable, and reducers which take state in action and give you the successor state. So things I like about Redox is it's incredibly simple. You can read the source code for Redox in the afternoon and you'll be going home early because it is a fantastically simple and well thought out library, and it fits what we do really well. And in particular, I think it's a very good fit for TypeScript because if you type your actions, if you take time to type your actions, so this is a slightly large union type, but this is the actions that can happen in the interface result, which we call the RTG is the in-theatre GUI. You have proper types for these actions. That means that you can be confident that when your reducer is called, it could be called from anywhere in the code, but when the action is dispatched, it has the right things in it. So if you look at one particular example, this local check result, that is the thing I keep coming back to, this check that we've got the same the image and the overlay correspond. This type here ensures that we've got all the information, and that means the reducer doesn't need to be very defensive. You just go, okay, right, so get to this, and you know that you've got a local result, and you can switch on that appropriately. So another thing we do is, because we've got this, you can log out the states and the actions, and from that log, we reduce this down. We produce abstract transition diagrams like this. So this is we found this is automatically generated from CI. This is a very powerful tool for reasoning about what the code's doing. So briefly because we're well over time now, but briefly, the black arcs there are transitions that we were expecting to happen. Blue ones are, and were observed. The blue ones are expected transitions that didn't happen in the CI run that we were looking at. And if there are any red ones, unfortunately, this is an acceptable output. For any red arcs there, that says, okay, you went from this state to this state via this action. Yeah, you weren't expecting that. So so that is something we can investigate, and we found actual problems and regressions have been introduced with this. So we introduced a circumstance where you can get this transition from between two states, which you weren't expecting. So we found that is very useful, and that all comes from the organising things in Redox with strong types, and just makes it a lot easier to reason about what you're doing. So, in conclusion, basically three things I think to take away. So the web platform is powerful enough for almost any application. So if there's an application you need, it would have historically been a native application. There's relatively few barriers nowadays to deploying that as a web application instead. And certainly, if you want to deploy things from the server, it's often a good choice. And you can use your existing sort of web development skills, and there's a lot to be said for the approach, and the platform is now powerful enough to support it. Second point, TypeScript lets you use that platform and develop more applications, more complex applications more easily than you would in JavaScript alone, just because it gives you the extra support and the extra structure to manage these large code bases. And the final point is static type checking combines really well with existing JavaScript tools to organize this complexity. So, right. So thank you very much. And I don't know if we have time for any questions, but yeah. Would anyone have any questions?
I'm just curious, what do you use for performance monitoring? Because you're going to have to check all the stuff in different browsers and things like that, and WebGL can be kind of inconsistent, like from performance in browsers.
So we use Selenium for CI testing. So we have a lot of Selenium tests for the kind of correctness. So there's performance. We actually in theory you can run this on. You can run the in-theater GUI in any browser, and it should be compatible with any reasonably modern browser. In practice, what we have, because so our original plan was we just get the hospital to provide the hardware, provide the browser, and there's no question that that's part of the device. But we found that produces too much variation. As you identify, there's a lot of variation in terms of things like WebGL performance, not just between browsers, but with different GPUs and the interaction between the two. So what we do for that reason, and for just reliability in general and testing in general, is we have a very standardized setup, and we will provide them with that PC to go into the operating room, because that's where the performance is critical. But for the desktop use, which does have some WebGL, I didn't show it, but there's a preview of the overlay that you can render in WebGL. For that, we check correctness using Selenium. We don't really worry too much about performance, because obviously there's so much variation in terms of machines and browsers that, yeah, I think we just accept a bit of variability there. Cool. Thanks.
My question is that most of the computation is done in the cloud.
Yes.
And network, inevitably, it's going to fail. And hopefully, well, not hopefully, but unfortunately, it might fail during surgery. What kind of fallback mechanism do you have?
Yeah. So that's a very good question. This is kind of, and that was a key thing which led us down the path of doing the correctness check locally. So even if you don't have the network, so the network can fail, but the correctness check is still running locally. And it means that if you have an overlay and an image and the image isn't changing, it will stay there. It doesn't matter whether the network's there or not. But as soon as the image changes and invalidates the overlay will come down immediately. So the approach is it fails safe. So part of our risk assessment is not showing an overlay isn't in itself harmful to the patient, because there are many reasons we might not be able to show an overlay. If the image quality isn't good enough, if they're pointing at the wrong bit of anatomy, or they're at too sharp an angle. We only work within a certain range of angles, so there's probably a wide range of angles now, but if you go beyond that, you won't show an image. So there are, so not showing an image in itself, we don't consider that a harm, but showing an incorrect image we do. So the key approach is we fail safe, and if the network's not there, we will maintain the overlay if we can, but if we can't, we don't get a new one, we just remove it. So. Okay.
Last question.
The JavaScript, the larger JavaScript ecosystem is pretty chaotic, and I was curious if you had any trouble with regulators about like using NPM, for example, because I feel like I would have, if I was a regulator, I'd worry about that. So.
It's a good question. Regulators, they tend to work at a more abstract level usually. What they worry about is you've got a process, and you've basically they want to know that you're looking at it rather than them looking at it themselves. So to the supply chain, fantastic term. So third-party software, term for it in the regulatory sphere is SOUP. Software of unknown provenance. which basically means anything that's been developed outside of your QMS, your quality management system. So we have to treat dependencies, and we have to basically review them and make sure that we're not using anything that's got either a performance problem, in that it's going to give incredible or a security issue. That's another big thing. Not so much for the medical device side, but we also have to think about information security because we're dealing with patient information. So how we get around that is we try and avoid dependencies as much as possible, and that was a big factor in the choice of Redox. So if you look at something like React, that has, I think I'm going to say, because it's conservative, say hundreds of dependencies. So that would be a problem if we wanted to include that into the in the in-theatre GUI specifically because it's a critical component. Redox though is almost entirely self-contained. When I said you could read the source code in an afternoon, I did as a basically to check it. And also the other thing that means I'm fairly happy with that as a dependency is if it disappeared tomorrow, we could probably have written a replacement in, or at least that served our needs within a week, because it's the thing I like about Redox is it's not so much a library as a concept. And there was a fantastic thing one of our team put on Slack a little while ago, was someone put re-implementing Redox in RxJS, which was literally a line. Because the power of Redox isn't the library so much as the idea and the notion of structuring your code in this kind of Redox style. So, okay. Thank you.